Hello everyone. I'll be giving a presentation about ALD for catalysis. Atomic layer deposition is a technology that's nowadays mainstream in semiconductor technology and getting more and more important with the progress of AI and more complex architectures. It is also a technique that has been used to make catalysts already for many decades and which is getting still more importance, for example, for its potential in the making of the single atom catalysts. This is a presentation I have given twice this summer, almost with the same contents. First at the UCRA-4 conference in Åland, so Unconventional Catalysis conference in Åland, Finland, and now in München in the first China-Europe Single Atom Catalysis Forum. And I decided that it's worth speaking the presentation into an online presentation and sharing with the world, because the audiences in the two conferences were very different, and then there's yet many people who are either working with ALD for catalysis or interested in working with ALD for catalysis who might find the contents interesting. So first I will introduce atomic layer deposition in a nutshell. What is it, where it came from, and where it is applied commercially globally. And then to ALD for catalysis, how it started in the world with focus on Finland, because Finland has been at the core of developing ALD, and that's where I come from also. Well, then some words on what ALD can do and cannot do for catalysis. In my view, ALD has become a little bit of a hype, I think, for catalyst preparation. So I want to maybe a little bit dampen the hype, although I do think that ALD is a very good method for catalyst preparation. Then for this online presentation, I will talk a little bit about our modeling about temperature excursions for ALD for the theoretical thin wall and thick wall cases. Those I had to skip in the real live presentations because there was no time. And then some words from my viewpoint about the future of ALD in catalysis. So quite some focus on the history in this presentation, because in the field of ALD, history has not been dealt with very well, and I do want to now share my understanding of how ALD for catalysis started, so that the scientists would all be aware of that. This might be the last presentation where I focus so much on it, or not, we'll see. But first about ALD in general. What is it, where it came from, and where it's applied globally. And I have here the photo of Tuomo Suntola, who is the Finnish inventor of ALD and who got the Millennium Technology Prize for his pioneering work in 2018. He's not the only one in the world who came up with ALD, but well, when it was time to give this prize, then the other inventors, they were no longer living, so it was a clear case that the prize went to him. But what is ALD? Well, the basis of ALD is in saturating irreversible reactions. Many people know them as self-terminating or self-limiting, but in fundamental chemical terms, they are saturating and irreversible reactions from gas to with a solid substrate, so adsorption. We have some starting surface, which must have some sites that are reactive with the gaseous molecules that we bring in. So ALD has typically at least two gaseous molecules that are brought to the surface one at a time. Here is, I'm calling them reactant A and reactant B. Here we see the reactant A coming in. So we have some starting surface here with those reactive sites. They are often hydroxyl groups, but they can be other sites as well. So here our molecule has been brought in, so the partial pressure in the vicinity of the surface or in the whole reactor reaction space basically has been increased, so that the molecules are coming to the surface. They are reacting with the surface, they are reactively adsorbing onto the surface. The adsorption can take place as the molecule as such, or although often a ligand gets removed through something that's often called ligand exchange reaction, and gaseous byproducts are released. And the reaction is allowed to continue as long as saturation of the surface takes place. So even when giving more time or more exposure to the reactants, the surface is no longer able to absorb more. Then the step 2 is removing the extra unreacted gaseous molecules from the surface. Sorry, I went further. And also the byproducts. So here the partial pressure is removed. There is either purge or evacuation, and yeah, basically otherwise nothing happens. The gas phase is just getting ready for the next reaction. And if we look at the mass adsorbed in total, well, it typically increases in the reactant A reaction. Most often this reactant A is a metal reactant, and these red balls here are supposed to denote the metal reactant or the metal atoms, the payload atoms. But if you look at then the rate of change of mass on the surface, well, that's going to be first increasing fast and then slowly, and then once saturation has occurred, then there's no change of mass anymore. Then it's time to bring in the next reactant. So reactant B, often a non-metal reactant. So in this cartoon example, which you can find, by the way, from Wikimedia Commons as an image with a CC byline license, so everyone can use this. And this was made for the Kirkotmer Encyclopedia article or chapter of ALD. We had the trimethyl aluminium water process in mind when we were drawing these cartoons, but this is a generic example of ALD. So reactant B comes in, it reacts with the surface that was left behind by reactant A, again leaving these chemisorbed species on the surface, again maybe, and in the case of TMA water, creating gaseous byproducts. In that process these would be methane, in other processes they are something else. And then again the surface gets saturated with the adsorbed species. If you look at the coverage of the chemisorbed species, of course, of those that were left behind by the first reactant A, those are going down to 0 ideally, while the reactant B species, they are going up. And again, there are changes with the mass on the surface. Here I am showing a positive change. Sometimes actually the change can also be negative. So depending on what are the masses of the ligands that get removed and what is coming on the surface, this can also go down. But when you look at the full cycle or sequence of steps, there, of course, in total the mass should go up, and if it's not, then it would be atomic layer etching, which is a closely related technique. So once you have made one full sequence of these 4 steps, typically, I mean there can be also more, but in this typical cartoon case there are just 4, then you can repeat those steps, those cycles, those sequences as many times as you like to grow a film. So this cartoon shows how we are bringing the partial pressure alternatively of reactant A and reactant B to the surface, how the surface is switching from one type to another, how the mass is changing, and here also this cartoon layer is increasing, but the end is always then looking the same after the reactant A and reactant B steps respectively. Of course, in the beginning of the growth, when you start growing on the substrate, this might look a little bit different than later. Well, I'll come to that briefly later in this talk. Okay, so more on this, for example, in the Wikimedia, in the Kirkotner Encyclopedia chapter of ALD, and of course I have written reviews also earlier. The Journal of Applied Physics 2005 review is one where these basics of ALD were described, and they were just a little bit updated for this encyclopedia article. Then about the history. Where did ALD come from? Well, the invention that most of us are aware of is in Finland by Tuomo Suntola, and he gave the technique the name atomic layer epitaxy. and he came up with the technique in 1974. You can read much more of the history in Chemical Vapor Deposition. 2014, I wrote there an essay in collaboration with Suntola about Tuomo Suntola's Atomic Layer Epitaxy. And also Wikipedia knows Tuomo. Very briefly, how was the first experiment? Well, Suntola came up with his target was to make thin film electroluminescent displays, flat panel displays that could be used in hospitals, hospital rooms, so to show the measurement data in small rooms where you wouldn't have so much space for big displays. That was his goal. And he started approaching this goal by making zinc sulfide layers on glass, so on transparent substrates. He developed a reactor where he had a rotating system where the glass substrate was rotated on top of zinc and sulfur reactant areas. They were heated to quite high temperatures, zinc to over the 300 degrees and sulfur to 100 degrees to get sufficient vapor pressure. And this was rotated 2 cycles per second, this glass substrate through those reactant sources. So this is the earliest example of spatial ALD that I'm aware of. And Suntola was following the evolution of the film optically, just looking at the color of the film. So he was expecting that the purple, or he knew in advance that the interference color purple means a certain thickness, and he was expecting to see those, and he was noting down as function of time when they were there. And it took some time before anything started happening, because they were expecting a monolayer of zinc sulfide per reaction cycle, but that didn't happen. The growth was slower, but things started then happening, and they happened linearly. So the purple color was coming back, and this was repeatable. So according to what Suntola has told me, they were first disappointed because, well, they were expecting this full monolayer growth, and that didn't occur. They had only 1/3 of a monolayer, and to me, to us, of today's perspective, of course, this looks like an excellent first experiment where you could get the film that you wanted. And Suntola's disappointment also then later vanished when he understood why it's not a full monolayer growth, but less. And the reasons for this, they vary depending on the process. Here, when it's just elemental reactants, it is surface termination and reconstruction related, whereas if you have the normal type of compound reactants which have ligands surrounding the metals, then it's also steric reasons for that the ligands take more space than the metal atoms, of course, and also related to the number of reactive sites on the surface. Again, more on the Kirk-Ottmer Encyclopedia or the Journal of Applied Physics, review 2005. Long story short, the development that was started, it was successful. About 10 years later, there was commercial production of these thin film displays, typically yellow-black displays, although 3-color displays appeared later. All right, that was the Finnish invention in very brief. But ALD was not only invented in Finland, it's been also invented in USSR, so not so very far from us. There was Professor Valentin Aleskovsky, who already in his I think this was his habilitation thesis, where he proposed the framework hypothesis, where he was considering the porous materials, how you can add materials to it, and how you can also remove materials from that. And this concept was in the 1960s developed into practice, where they modified typically porous silica with chloride water type ALD processes, so titanium tetrachloride water. It's reported already in the 60s. And here is a later example of they have applied a sorbent in some real applications, and they have also scaled up their catalyst synthesis or sorbent synthesis. I'm not sure which one this is. So this is a picture from 1982 with young scientist Maligin, nowadays Professor Maligin, uh, looking at the I guess this is a spatial ALD type of particle coating system that they had developed. And if I had written this, I'm sorry, this history of ALD from Suntola's perspective, then Maligin and colleagues wrote a similar essay about the history of the molecular layering technique that was developed in Leningrad, USSR. The molecular layering is of course English, and they didn't write primarily in English, but in Russian they were calling it molekulярное наслаивание, and it has been translated into English in many ways, but the most typical one is molecular layering. And also many of their works have been published first in Russian, but there have been these official translations into English already early on. Okay, so ALD was separately invented in Finland and in Russia, or in USSR. How did the international community, or how did people learn about each other? Well, I'll present the Finnish point of view. So it happened that Professor Lauri Niinistö, late Professor Lauri Niinistö, organized the first international conference on atomic layer epitaxy in 1990 in Espoo. And as you can see, you can read further in this blog post here, this person in the picture, Viktor Drost, came there from Leningrad and presented their work and made the first contacts. Also Jan Aarek from Estonia came. And that's where the first contacts were made. This Viktor Drost came to some other conferences also. This is from Austria, Linz, the fourth Atomic Layer Epitaxy conference. And here you see posing in the same picture, there's Tuomo Suntola, Finnish inventor of ALD, Viktor Drost, who was working with Alekskovsky, Professor Lauri Niinistö, who was at Helsinki University of Technology, starting ALD, and now Professor Emeritus Leskelä, who has made a career at the University of Helsinki for ALD. And here's also Stephen George from University of Colorado, who obviously all have been in the same place at the same time, as testified by this picture, which is also part of their essay. And so personal contacts were made. And I started my career in ALD in 1998. I made my master's thesis to microchemistry, and that took me to the field, and I have never left. I made my doctoral thesis soon after, and actually in 2002, and then in 2002 also this book chapter by Ritala and Leskelä appeared, where they have a table and they present alternative names for ALD there, and one of the names is molecular layering, and it said that it dates back to old Russian literature. I found this very interesting as a young scientist, and during my postdoctoral time at IMEC, I digged further into this. I had the two questions in mind. Is it really exactly the same as ALD as I know it? And well, I also wanted to know when, because well, it was interesting to know if it's older than the finished work or younger. And I found the answers to these two questions. So yes, it is exactly the same technique, and it is older indeed. So I found the first works from 1960s. And I found a lot of other works. I think I found more than 100 papers in English And when I wrote a review article 2005 to Journal of Applied Physics, there I presented table 1, some Soviet-Russian ALD investigations, to present these to the world. Because even though people had met um, the reviews that had been written by the people I knew, they never really talked about these USSR works. So this review by me from 2005 is the first one that really exposed those works. And yeah, there is a significant table about them, but I was aware that it's not the full story already when I was writing the review. That's why there is some Soviet-Russian ALD investigations. And I hoped that this would change our field, that people would further dig into that. But it appeared that this didn't really happen so much. And then many years later, 2013, we started jointly with some other scientists an effort to really find out about the history, to clarify the history of our field. And I started coordinating the virtual project on the history of ALD, which has also, or had, and still has a website, vphald.com, worldwide collaborative effort in atmosphere of openness, respect and trust. And this is where we collaborated with more than 70 scientists from more than 20 countries to collect early works until 1986 together and read them and understand what's there. And we have created many presentations, and there are 4 publications directly related to this history project. So these 2 essays that were already mentioned, then there is a review with I think 62 co-authors that has a recommended reading list of early ALD publications, and then I also have an invited contribution in ECS Transactions 2018. So there's a lot of information, but then another point is that I would say that the general view in the field, in the scientific field of ALD, it has only partly gotten updated. I have been a little bit astonished of how slow this change is. So going back to what I already showed, 2002, there was this chapter in a book by Ritala and Leskelä telling that molecular layering dates back to old Russian literature, and then I found about that old Russian literature and shared it with the world. But then there is a major review was published 2010 by Stephen George, and this information had not made it to that one yet. So it's 5 years after my review, but there is no mentioning about the USSR roots there. And a few years later, there was a AVS ALD history review published with Greg Parsons and other top level scientists of the field. Then altogether, they mentioned the molecular layering a little bit, but very poorly, and they had to write an erratum specifically about that part. That took 7 years to get out, and I've analyzed it in the history blog a little bit because it's actually a little bit difficult to read. And then 2 years ago, 2024, the ALD conference, AVS ALD conference, was again organized in Finland, and that was then 50 years since the invention of Suntola, and it was great to have a talk by Tuomo Suntola about his work, and of course it was 50 years of ALD of him at that time, but then it was already 60 years of ALD in general, and this completely remained unnoticed at the conference, and where the chairs were the same persons who wrote that book chapter 2002. So 20 years later, there hadn't been very much changed, and also there's this Atomic Limits website by TU Eindhoven, Erwin Kessels, where they also presented a brief history of ALD, and they also defined it to start from 1974. Well, I know that the history starts from much earlier. And when we started this virtual project on the history of ALD, we started it in 2013 at the AVS ALD conference, and the same year I got the opportunity to travel to St. Petersburg and actually meet this Professor Molygin, who was in the 80s looking at the scaled up particle reactor there, and many other scientists. And I met a lot of people and gave also a presentation to the group of Professor Molygin, and there were about 20 ALD scientists there. And after my talk, the first question that I received from the audience was, why have our works not been cited? And I did find it a valid question then, although of course I have personally tried to cite them. But having seen how slowly things get updated, I think it is a valid question still. And yeah, here is an example from the Millennium Prize news. How, I mean, of course you can credit also others, even if it was a prize for Tuomo Suntola, it was very fair to acknowledge that there is this other route also, and it's nicely explained there or mentioned there. Okay, now back to today or a few years ago. Where is ALD applied globally? When we created this chapter to Kirk-Ottmer Encyclopedia, we went, or specifically Ruud van Ommen, went through the information about public applications of ALD, public commercial applications. And we made this summary for that. It's possible that there are more, but we only wanted to highlight those where we could really trace back that ALD is commercially applied. And the first one was the thin film electroluminescent displays, where both the phosphor and insulator films were made by ALD, probably passivation also. And so the production started in 1980. Now I'm not sure, was it 5 maybe? And this product cycle has come to completion or conclusion because that production was stopped 2-3 years ago in the end of 2023. Then ALD is used also in the memory chips and in the logic chips, the transistors of modern semiconductor devices. This is a very simple example of a transistor. Nowadays they are of course already these gate-all-around transistors, and ALD is used for dielectrics and barriers and metals and lithography and many things. And I've understood that the modern semiconductor device has tens of passes of ALD when it's manufactured. Then also the magnetic read-write heads of hard disks. These were already earlier than the semiconductor applications. Also passivation coatings. Silver objects are passivated with a thin layer by ALD so that they don't get darker with time. And a big application is also solar cells since a few years. And there have been some news that lithium-ion batteries would already be in commercial production, but those we couldn't trace then for the chapter, and I haven't seen really the convincing data yet to be able to say for sure. But then let's continue. How ALD for catalysis started in the world. So now this picture that has been taken at the Millennium Technology Prize event where Suntola got his prize, it has gotten another face. And that face here, it's by Outi Krause. Outi Krause is a professor emerita of Aalto University. At that time, she was working at Neste Oil Company in Finland, and as told in the Suntola story, Suntola started microchemistry. Now I don't remember, was it 1987 maybe? And Neste was also owning part of microchemistry, and the Neste leaders were telling Outi Krause that she should contact Suntola. And she contacted, and the first meeting was in April 1988, and meetings continued, and they decided that they would do a first test, and the first test was for zinc, again evaporating elemental zinc, on ZSM5 zeolite. And this was a test made for aromatization, and the results were quite promising, and they got the permission then to continue, and that led to also a patent application. And here you have the details, and you can look back more if you want. The patent was applied in January 1990, and in addition to zinc, there's also, for example, chromium on silica for ethylene polymerization. And this history hasn't been really written earlier very well, so there are already 40 and more review articles that deal with ALD for catalysis, and none of them have reported these. So the best sources now are by Lakomaa et al. A chapter in the book Catalysis in Finland, that's from 2013. Also the Suntola essay, and then for the new review on ALD for particulate materials in Chemistry of Materials this year, 2026. There is a section about ALD for catalysis where I have written out some of these details, and there are also some footnotes, as I remember, specifying the details. The work continued. The next patent was filed in summer 1991, so 1.5 years later. And what I have found important for tracing back the history is that you remember the first atomic layer epitaxy international conference was in 1990 in the summer in Espoo. So the meeting with between Drost and others had already happened, and Suntola had visited St. Petersburg, and some others had visited it as well. And this patent then, which is after that meeting, it already cites back Kautsov's work. I find that very interesting, and it's matching everything that has been told to me. The first scientific article appears to be about the kinetics of toluene hydrogenation catalyst on supported nickel catalyst, and this is by Tapio Salmi, Åbo Academy, and his student Lars Petter Lindfors. Here we don't see Outi Krause in the author list, but when you look at the acknowledgement, it's clear that also the same Outi Krause who initiated the work has been also important for initiating this work. And then there are other papers appearing in the 1990s from Finland, and one that I would hope that all of us who work with ALD for catalysis, and why not other particulate materials as well, would be aware of, this by Eva-Liisa Lakomaa. It's a kind of a review type of work, but it was not really a review because there was nothing to review yet, but or maybe a perspective, even though it's not called like that. And there Lakomaa is telling about 5 ways to control the metal loading that you get by ALD, and this is a really good description. These are still valid today. So you can control the number of bonding sites, typically OH groups, by heating the support. So if you heat silica up to about 700, you have about 1 per square nanometer of OH groups. You can, to decrease the loading, if you get too much in one cycle, you can block reactive sites. And this is something that's nowadays done a lot for area selective ALD. It has been used for catalysis already long ago. You can of course also play with the reaction temperature. It affects sometimes more, sometimes less. Of course you can then change the reactant. Some some molecules are more reactive and more bulky than others, and if then to increase the loading, of course, doing the ALD cycles is an option. So these were already described by Eva-Liisa Lakoma in 1994. All right, then how ALD for catalysis started in the world. You see the note skip. I didn't have time to talk about these in the presentations that I gave, but now I do. So in Leningrad, nowadays St. Petersburg, but then Leningrad, USSR, the molecular layering work started. And in the virtual project on the history of ALD, we were collecting information about the early publications in what we call the ALD history evolving file, which is still available and will remain available. So here is information copied from there, and this is from the translation into English of the paper that was originally published in 1970, first in Russian in Kinetics and Catalysis, Kinetica y Catalysis. And it was about the influence of the carrier on catalyst properties, and the scientists in Leningrad, they were adding phosphorus and titanium, modifying silica with those, and doing carbon tetrachloride hydrolysis. And then there's a follow-up paper a few years later where they were changing the order of this ALD modification of silica and found that that affects the catalytic activity. And these are real scientific articles. There are some conference abstract already from 1960s. And other papers that we can find in this ALD history file, there have been more papers, more metals, more applications, oxidation, catalytic cracking, polymerization, also modeling of fluidized bed ALD. And then there's a thesis from 1979 where zirconium, chromium, silicon, titanium, tungsten, vanadium, phosphorus are mentioned as being made by ALD. So this was significant work. And yet we have found, when we made the review for chemistry of materials with collaborators from TU Delft, the Netherlands, that also in Japan there are early publications which probably have been made without knowledge of the other early works. And there is this name Iwasawa that Iwasawa, yes, is in all of these, from University of Tokyo. And they have they have made isopentane from methanol on zirconia on ZSM5, also zeolites then, and some other reactions as well. And these are also works that are relevant, and they have remained not much cited. And here I really have to give credit to the colleagues from Delft, especially Aris Gulas, who was able to find back these works. And this picture is from the review that I already mentioned. There we have made a systematic analysis of ALD on particulate materials, and then separated those per application. And this graph shows the number of publications per year that relate to catalysis. And I think that it's really easy to see here that there have been 3 eras of ALD for catalysis. First, there were the Russian publications, and also some from Bulgaria. There's also a habilitation thesis from Bulgaria that was in the 1970s, 1980s. Then there's the Japanese publication appearing. The Finnish era started. There were quite some works. My thesis works are also here. Then Belgium appeared, and there was a little bit of activities, but there was also a moment where we haven't seen any publications. And then clearly things have happened, and there's now much more countries, much more publications per year coming in this. And first, clearly the United States was coming up, and clearly thereafter China, and actually South Korea has also appeared even earlier. And Finland is here still, here and there, publications from me and someone else maybe, but no, it's clear that the China is now the global leader, and ALD for catalysis is much bigger than it has ever been. So those who are following this presentation, it's most likely that you are representing this third global era, but it would be important that you would be aware also of these earlier works. Because as scientists, we should know, of course, and we should give credit to those who were earlier. All right, what ALD can and what it cannot do for catalysis from my own perspective. This is a summary of how ALD is applied for catalysis that we made for the chemistry of materials review. I'll go through the cartoon quickly. So of course you can grow compound materials, so oxides, nitrides, and so on porous materials that are here just represented by this substrate. And you can make then metallic materials by reducing those. Sometimes you can also directly grow metals, but it's much more typical to grow oxides and other compound materials by ALD that kind of fits the scheme better. And this is how the very first examples from Finland were. There was nickel grown from nickel acetonate, I think, and then oxidation with oxygen at higher temperature, and those were reduced to nickel on alumina and then tested for hydrogenation reactions. You can also grow a wide variety of mixed compound materials, and this is how they started in Leningrad. They had the different vanadium and phosphorus and titanium and so on that they were mixing from early on in a pretty elegant way. One can also imagine to change the surface termination. So if you have a material that it's difficult to obtain in high surface area form, you may imagine that you create a thin surface layer on a high surface area scaffold and then use that to place your catalytically active materials. This is how I did my thesis in 1998 to 1999 to 2002, where growing aluminium nitride was the goal, and then we placed catalytically active metals there. You can also play around with selective growth, and this is probably something that's going to become more important in the future. So depending on your process, if you have already a metal on a support, you may add materials either so that they go everywhere, or you might have selective growth on the support, you might have selective growth on the metal or even some certain sites on the metal, or you might be able to grow these core shell particles, but depending on the process, you might also end up having mixed metal particles. You can also grow overlayers by ALD. For example, alumina has been often applied this way, but also other materials, and it has been interesting to follow that it's still possible to have the catalytic activity even though you have partly coated also your particles. And then something that I found from the literature from the new US period is this using temporary ligand protection to the metal so that you can then keep on growing the layer and then you expose the metal only later. So please see more details in the chemistry of materials review if you like. I'll give two examples of how to apply ALD for catalysis. Here I see I have the picture of Yungling Lu. I hope he doesn't mind. He was at the single atom catalysis conference and has been working with ALD for almost 20 years, ALD for catalysis. Here is perhaps one of the most known works of ALD for catalysis. This is from the Science Journal, right, 2012, where exactly this overlayer has been grown on palladium on alumina, and the overlayer was also alumina. where this overlayer has protected the catalysts from deactivation in two ways. So this oxidative dehydrogenation reaction with overcoated catalysts worked, whereas it really didn't work with the non-overcoated normal ones. And you see here that if you examine this further, that in just the normal catalyst, there was a severe problem of coking and also of sintering, whereas in the ALD coated ones, both of those are absent. So the particle size has remained small, and you can also not observe those whiskers. And another example is from our rather recent work from my group. So we have added zinc on CO2 to methanol catalysts, where we first added, no, well, this is still about zinc on zirconia. Next one is about catalytic results. So we developed a new process, zinc ACAC and air oxidation at higher temperature on zirconia. We have taken SEM EDS cross sections to see that the zinc actually is through the zirconia. Here we show the signal of hafnium to show the support. Zirconium and hafnium always go together, and we show here how much zinc we have obtained as function of ALD temperature. There are for the same samples always at least two samples, same processing batch, always two samples, and we get roughly 2 zinc atoms per square nanometer. In all cases, when the temperature goes up, we start to get a little bit more, but otherwise this is really flat here. And then the question about tuning the properties of the support. So we have also calcined the zirconia at different temperatures, and we see that the zinc loading that we get, it's going drastically down with temperature, but so is also the surface area and the green points here. And if you then look at the amount of zinc per unit area per square nanometer, again, we have in all cases roughly 2. So irrespective of the ALD temperature in a small temperature limit window and the surface area, we get 2 per square nanometer. So it probably means that it's the steric effects that are limiting the amount of zirconia there, and not that we would be running out of reactive sites. Then we have made a test where we were heating in, I think, synthetic air the sample, and we found that once we are at 400 and beyond, we don't get any more the oxidation products. So we made 3 cycles, and we again got roughly 2 per nanometer square per cycle. And from low energy ion scattering, we could see that after the first cycle, basically all the zinc atoms covered the zirconia. So we could probably say that we had single atoms, although we don't know if they were next to each other, but they were at least not on top of each other. But then in the further cycles, we didn't cover so much anymore. So probably we then had more like zinc oxide particles. And quickly about catalytic testing, published in Applied Catalysis B. We tested different locations for zinc. We also tested copper on zirconia without zinc, and then zinc on zirconia without copper, and then various combinations of where, if we place the zinc before copper impregnation, or did we impregnate copper first and then add the zinc. And in one case we did both, and we found, long story short, that adding zinc as the last step was favorable. So we had both the highest conversion of CO2 and also the best yields, best production rate of methanol in those cases. So the blue points here, they represent the cases where zinc was last on copper. And also the selectivity was best. Yes. All right, what ALD can or cannot do for catalysis? So there is quite some promise in this selective area growth, and but it's still important also to understand that you don't necessarily get what you wish, but it's the nature that defines. So it is the reactant pair and the substrate surface and the temperature that really define where your materials grow. So you might wish for one thing and get another thing. So you need to check. There are quite some misconceptions around ALD. One is that you would get full monolayer growth per cycle. This was the expectation of Suntola, who already in 1974 learned that that's not the case. Still, people are often expecting that. It's almost never the case. For the review in chemistry of materials, we actually went through the growth per cycle values, and we found that the maximum we could that had been reported was 7 metal atoms per square nanometer, which is roughly half of a monolayer, corresponds to roughly half of a monolayer. Typically, it's a little bit less even. And then once you get this less than a monolayer growth on the surface, so it can't cover the surface in one cycle, you need more cycles to cover it. Still, this growth mode A, the layer by layer growth mode, or the two-dimensional growth mode, is the one that people often expect for ALD. Reality may be different. You might have island growth. You might have island growth that starts from defects, and if there's no surface diffusion, then you will keep on growing those defects. Of course, they will then later form a continuous film that covers the substrate fully. But then there are some processes, especially in the noble metal ALD processes, that are based on oxidizing the ligands and then reducing the noble metal right away. One can have already particles, nanoclusters of particles, even after one ALD cycle or sequence. And that's important to know for example, those who aim to make single atom catalysts by ALD. So you might not have single atoms even after one cycle, although in cases you might. And also for those who work in catalysis, now I haven't cited anything for that, but it was already described in the 2005 review how adding the same areal amount, so amount per square nanometer, for example, it actually does not correspond to the same added weight percentage when you increase the cycles. In addition to that review, there's also a great paper from the Baskat group from Berlin who have shown this. Now I don't have the reference here though. And also the growth per cycle does not need to be constant. There's an expectation often of constant growth per cycle, but of course it can vary. You start from one surface, you end up growing another type. Of course, the nature may define that you have a different amount that gets absorbed here than after many cycles. And by the way, this scheme, it's new, it's very recently published into Wikimedia Commons, and here, so the different growth modes are illustrated, and I have made a case where we would have just one cycle, 5 cycles, and 10 cycles with defined growth per cycle values. They are 1/3 of a monolayer for the first, second, and the last example, and the island growth example has a little bit less, but they all have the same constant growth per cycle assumed. Okay, single atoms. So this is where I hear that many people are interested in ALD at the moment, and in favorable cases, ALD can of course be a really good method for making those, but it is possible, depending on the conditions, that already after one cycle you actually have clusters. And here I have cited, I think, well, maybe among the much cited early single atom catalyst works from ALD, and one is from Jungling Lu, where they already then noted that in addition to these atomically dispersed palladium atoms, there were already palladium nanoparticles present. So there's promise, but you need to check. And one thing that I do want to tell for anyone who is interested in ALD for catalysis is that when you work with porous materials, when you work with catalyst supports, ALD will necessarily start as a coating from the outside that then penetrates deeper inside. So you get an eggshell coating always in the beginning. Many people have, to my understanding, assumed that because it's ALD, you would have conformal coating right away, but that does not come automatically. That needs time and that needs a higher amount of exposure. So here are examples of a nice uniform distribution already from my doctoral thesis works 2002, long ago. TMA ammonia process had been used and we got a nice constant aluminum to silicon ratio through the particle. Here is a work 20 years later where TMA water had been used, I think, on titania, and there was cobalt that's impregnated, that's all true, but the aluminium oxide coating is only on the outside because the process had not been tuned to have it throughout. Then there's yet a newer example. This is collaboration with TU Delft, where we made platinum ALD on alumina spheres that were of different sizes. I think these might be for 1 millimeter size, although I don't remember for sure. And clearly we had first an eggshell coating, but when we elongated the exposure times, yes, to over 1,000 seconds, then we had the coating throughout. And we have also simulated these through diffusion reaction simulations, and those also show the eggshell coating that then goes through when we have enough of exposure. Exposure meaning partial pressure times time. And what I think where ALD will be powerful for scientific research, where you want to have the same kind of surface on planar and porous substrates. So if when you are making your porous material, if you there in the same reactor at the same conditions have pieces of silicon, for example, present, to my understanding, you should have the same coating in both cases. It does not work the other way around, that you would place your porous material next to an optimized um, thin film process, because there the very likely the exposures will be too small for the porous material to get coated, but the other way around should work. If porous material gets nice coating, then also the flat wafer will get it. And one thing that I didn't have time to talk about in those two presentations that I gave, but ALD, it's based on adsorption, it's based on chemisorption. Chemisorption is exothermic, and ALD reactions are very fast. Good ALD processes are based on fast and aggressive reactions, and that means that there's being heat released in significant amounts. Also this year we have a CFD paper out jointly with collaborators from Aalto University, and these CFD calculations were made for cases that are relevant for both semiconductor field and catalysis or other particle-based fields, and they simulated so to say, thin wall and thick wall conditions. And the thick wall conditions, they would correspond to, well, wafers, for example, silicon wafer, where you grow a layer. There is, of course, heat is being released in these reactions there as well, but there's the mass of silicon to absorb it, so you don't really get a much higher surface temperature through that. But if you have a thin wall condition where you have much less material that could absorb the heat, then you will increase the temperature of the system. And in these calculations, even 200 centigrade or Kelvin heat temperature increases were simulated. And is that realistic? Well, this has not been paid attention to very much in the literature, but a few years ago we started thinking of this, and some others as well. Here is a paper from Greenberg et al., where they have measured for particle coating a 20-degree increase, and we have at Aalto built our ALD reactor, and this is from a master's thesis 2 years ago, where we have observed that once we start delivering our reactant, this was zinc acetyl acetonate in that case, we do get a temperature increase, and in the highest case it was 40 degrees increase. So this is clearly something that should be paid attention to, especially when scaling up ALD reactions, ALD processes for powders. Okay, future. What do I think about future? Well, I think that ALD will remain a very strong tool for making fundamental scientific research in the field of catalysis. And the fact that ALD is being used so massively in the semiconductor technology, it helps also the ALD for catalysis, because there's quite a lot of funding for also from companies for developing new processes, new reactants, and of course they then apply for all applications once they have been developed for the semiconductor field. For catalysis, it's important to pay attention to the distribution. I'm actually quite worried that there might be quite many papers out where people have assumed that you have a uniform distribution throughout, simply because it's ALD and ALD would give it. But if the process hasn't been tuned for that, then it might be that you have an eggshell only. So you need to demonstrate that, in my view. I would hope that the field would start reporting systematically and always the metal loading also as atoms per square nanometer, for the purpose that then it's easy to compare processes, then it's easy to understand also, because this 1 square nanometer, it's a very good measure, because it can populate about 10 or a little bit more atoms, and it's easily understandable number. And also those who are doing computational chemistry, DFT and so on, they also can access exactly the same thing, how many per area. So I would wish that to become a unifying measure. And of course, when you do thin film ALD, you can also calculate this number. How about commercial breakthroughs? Well, yeah, that's many have wishes for that. I don't necessarily expect ALD to make breakthroughs for catalysis, but it's not impossible either. And so if conventional techniques can't do the job, if there are creative scientists that make catalysts that do actively convert desired compounds to still more desired compounds, and they are stable, then maybe there are chances for that. And of course, there are now 2 companies in the world that are doing the scale up very seriously. So then if there are these breakthrough catalysts, then yes, they can be scaled up. I would wish more open science in our field. So my group has published codes to GitHub, data to Zenodo, and also there are some collections of literature in Zotero, some open Zotero groups where anyone can join. I would wish there to be a collection of ALD reviews. There is now, but it's not complete. We could do much more on this, and also, well, I'm interested in publishing well curated and well planned data sets. So I hope that many will join to this, and of course, making this presentation public, it's also a part of this open science attitude that I want to progress. And then acknowledgements. Current funding to my group comes from European Union CHIPS joint undertaking Genesis, and also Research Council of Finland, the INCUT project. And I do want to thank all current and past group members who I didn't start to detail here by name. I am very grateful for Tuomo Suntola and for Outi Krause for the support over the years and decades. Suntola is still active as a scientist working with his hobby, the dynamic universe, and Outi Krause is Professor Emerita from Aalto University. And so this picture is from the Millennium Prize event, where I had also the honor to participate, as I had written the nomination in the name of Aalto University. I'm thankful for the organizers of the UCRA conference for inviting me to talk about ALD. I'm likewise grateful for the organizers of the first China-Europe Single Atom Catalysis Forum, for inviting me to talk, and I am very, very grateful for all who have contributed to the ALD History Project, the virtual project on the history of ALD. We were more than 70 from more than 20 countries, and that work has been really important for the field. So thank you to all of you. And continuing on that, there is the website for virtual project on the history of ALD. It has been up, I think, from 2013, although I don't remember for sure. And I've decided that it's time to let it go. I have kept it up personally, and there's of course a cost every year. And now I think we don't really need it either anymore. It was a collaboration hub for the project. The project is over, and we have achieved what we wanted, so it can now be terminated. So in August this year, probably it will disappear from existing. There is also the ALD history blog. That's from me privately, without any cost associated. I will keep that up, and I will also welcome if someone wants to write a guest post of their view on the history. I will be happy to receive such. And what I'll do is I will go through the contents of the website, of course, the one that's going to go down. I have already copied these 5 pages. They exist now in the history blog just as copies as they were 2-3 days ago. And I'll go through the materials also and save, but I don't know yet how and where. So if there are people either who collaborated in the VPHA or otherwise, then you can of course download contents also for your own use, and now there's some time still to do that. And for anyone who listened to this presentation, I thank you for listening, and I wish good luck for your ALD related works, and I'll be happy to discuss these themes later in conferences and where we can meet. Thank you.